So I'll tell you a story.
Yeah.
A small creature of speech.
You can't leave it open though.
First of all, I don't expect everyone in the audience to actually know what is the thing called Sphinx. It's a full-text search engine, open source, blah blah blah, and so on and so forth. All the usual stuff that you'd expect to hear on the MySQL meeting. And the reasons for the first question after you hear, blah blah blah, free and open source and whatever else search engine is possibly why should I ever use it? So the reasons is I see them are as follows. First, it's pretty good at indexing and searching, delivers pretty good performance, and delivers pretty good relevance, at least we hope it does. And it scales well, and it has done a lot of features, and perhaps the most funny thing that I discovered during the development of Sphinx is that it actually can improve non-full text queries, and is sometimes used to offload certain types of queries from MySQL to Sphinx. I'm not sure if we'll have enough time to cover that in this session, but we'll even see. So we do already have MySQL built-in. MySQL is built-in full-text search, and we have Lucene and Solr and T-Search and Megasearch and all the other kinds of search engines. Why do it in Sphinx? Well, you don't. Actually, you don't. As long as MySQL full-text search works fine for you, as long as it scales well up to your vast 100 rows of data, you're fine with MySQL full-text search. As long as its relevance is good for you, well, good for you. But at some point in time, at some point in the project's life, you might just come at an issue with perhaps the performance of the full-text queries, perhaps the relevance, perhaps all of that combined, and Sphinx just might do the trick. Well, then again, maybe it won't, but at least it will try. Now, to give you some specific numbers of, to give you some specific performance figures, it's typically much faster than MySQL's built-in full-text search, except in cases when your data set is so teeny, it fully fits in RAM along with all the other indexes, and in those cases MySQL performs well good enough. But once MySQL's full-text indexes start hitting the disk, it degrades to an awful condition. I'm not sure whether everyone used MySQL's indexes, but moreover I've seen them hit the disk, but it's not unlikely to have like 3 minutes for one row insertions or 20 seconds for typical search query to complete, so it's barely acceptable for a dynamic enough project. It's also sometimes faster than MySQL even for regular queries that touch a lot of data for full scan type queries. I'm not exactly sure what is the reason for that, but we measured about 4 to 3 times difference in scanning 2 million of rows and just sorting them, picking 10 best ones, grouping by sub-column and sorting within that group and sorting the groups, and that was faster with this Sphinx than regular MySQL. It's also faster than Lucene, but actually I believe that sorry, my English dictionary just slipped out again. I think that the bigger reason to use Sphinx is not actually about the performance, because nowadays with beefier and beefier machines and clusters serving everything, it's not that much about performance, but rather about the quality of results, the relevance in the full-text search field. And speaking of relevance, most if not all other open source systems that I'm aware of only use so-called BM25 ranking function that only accounts for statistical properties of the query. It only takes into account the frequencies of the keywords within the query, within the document, within the entire document collection, but not the unusual positions of the keywords. BM25 based system is not going to rank the exact query phrase as it was entered by the end user of your website or internet site or whatever. It's not going to rank it any higher, even though it's a verbatim quote from the document. Sphinx is going to do that, and actually that was the reason why I started it, because back then in 2001 I had a small 100,000 euro collection of lyrics, and I was impressed by the fact that I have a 100,000 lyrics stashed on my hard drive, and I'm not able to look up a song that I just heard on the radio by simply inputting the text and searching for it. And no other system let me do that. And BM25 systems were actually not ranking the results that I knew were there. They were not ranking the results nowhere near the top. And skills as in, well, blah, 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 you see the numbers, yes, it's billions, you can have billions of documents, millions of queries per day. Well, I believe it can scale. Now, okay, perhaps some of you are still interested to hear more about the insights, how it works, how I use it for my website, so let's proceed to that. The typical workflow, let's dissect the workflow. We did have a couple of programs. We have a separate program that does all the indexing, that pulls the data from your database or whatever your data source is and builds the full text index. That is then possible to search through another separate program, a search daemon. So that's the mighty couple. And how do you index the data? You create a simple textual configuration file. You define a data source. It's basically an SQL query with some bells and whistles, but in fact it can also be something in XML format coming through a pipe to the indexing program. You define an index, which is basically just a path in the file system where Sphinx will store the data files plus some tokenizing settings and stop words and stemming settings and so on and so forth. There's plenty of settings that you can use here. You run the indexing program, it builds the indexes or rebuilds the indexes, and this is it. This is the most simple configuration file sample I could come up with. So you have the query, you have the attributes, you have the timestamp attribute defined here, and floating point attribute. This is it. And if you want to go, if by any chance someone wants to go deeper than that, Sphinx index is a typical inverted index, meaning that for every keyword we keep a list of documents associated with that keyword. We also keep a list of all the infra-document positions of the keyword for the purposes of phrase matching, proximity matching, phrase-based ranking, and so on and so forth. And the index is built in two phases. The first phase is collecting the documents, fetching the data from database, tokenizing the data into specific tokens according to the settings that you configured for your particular index. Well, taking into account the character set that you want to use, the tokenizing exceptions if you want to, for instance, normally treat plus as a separated character, but still index C++ as a valid keyword. That's something job sites do very frequently. And the second phase is the final sorting, where we build the fully sorted index, fully sorted by the keywords, and so on and so forth. And in just 5 minutes of magic, we build the index. How do you perform the searching? you launch the search daemon. Well, actually, normally you keep it running, and you can query the search daemon through a number of interfaces. We could provide native APIs, pretty lightweight native APIs, maybe 30 to 50 kilobytes of code each for a bunch of different scripting languages. We also provide a bundled pluggable storage engine for MySQL that you can use to access Sphinx. And last but not least, maybe around a week ago, we rolled out a version that lets you use MySQL interface to connect to Sphinx. Sample 1, native API. 3 lines of PHP code, wham bam, we do some searching. Sample 2, how do you search using that strange magic Sphinx storage engine? And what is it, by the way? Sphinx storage engine is just something you either compile into MySQL 5.0 or dynamically load into MySQL 5.1 and then use to access Sphinx from inside MySQL. Why would you use that? Yes, you. Aha, no answer. But I do know why. Okay. I need some fuel.
You would use it because you want to be able to just query it, right? As opposed to...
No, that would be too simple.
Okay.
In fact, if you just need to get a few rows of the search results back to your application, you don't normally need Sphinx storage engine. It's just an extra level of complications and hassles of compiling something and getting it into your MySQL binary, which might be less controlled, or I don't know, for Christ's sake, web means controlled. Too much of a hassle. But if you need to post-process the search results set on MySQL side, if you have too much rows, for instance, if you need to pull maybe 10,000 rows and then sort them by something you don't put into Sphinx, you don't have on Sphinx side, for instance, on maybe on book author or on something stored in a separate join table or on a complex combination of joins, then you just might need Sphinx storage engine. And this is a sample of how that magic works. You select something from Sphinx table, you join that with your original data table, and Sphinx storage engine intercepts the where clause on the query column of the Sphinx storage engine driving table, and it fires the query on search engine side, it pulls the results back to MySQL, and it makes them available within MySQL without the overheads of first the results back to your application, and then having to push them from your application back to MySQL. And
so you basically want to say that like sorting will happen. A second example, sorting will happen on the Sphinx side, right?
Exactly, and this is why the second example is cynically dubbed better, because in the first example, you'll pull all the rows from Sphinx table to MySQL side, then join against your product table, then order them by price. This is slow, because joining against the table in MySQL side and sorting it is unfortunately slow compared to having Sphinx sort the results based on the attribute data that you indexed, that you put into the index on the previous step when you were creating the index. So the second route is better because it lets Sphinx do the sorting on its side, and it's much more faster when it comes to big enough result sets. Say you don't care as long as you have 10 rows. You do care when you have 1,000 rows. Finally, the most interesting feature of it all is MySQL interface. We implemented the rolling subset of MySQL protocol. We implemented our select query, and this is it. This is how it works. Not the server version, not that MySQL is not even running on the box. Well, was not even running on the box by the time the screenshot was made. So from now on, you can simply use the regular MySQL client to connect to Sphinx daemon, and you can use the regular select syntax to run your full-text search queries, except that we don't use mesh against we just use simple match clause, and the string inside should be in Sphinx query language syntax. And also we add a bunch of extra options, extra Sphinx-specific options that let you choose the ranker, choose the ranking algorithm, choose the field weights, the index weights, and so on and so forth.
Wait, now can you use it at the MySQL client only, or can you use any of the connectors or the native C API? Or?
No, we just implemented everything from scratch. It was very simple.
But like I could have a Perl program or PHP program that connects the same way?
Yeah, sure. I mean that search daemon implements MySQL network protocol. It pretends that it's a MySQL Z binary running on the given port and accepting connections and so on and so forth. We actually don't limit ourselves to select. We have a number of other clauses, and once we implement the real-time updates, we'll definitely implement insert and update and delete. And I already feel the urge of implementing show indexes, because every time I connect to my own test instance of search daemon with MySQL client, I don't remember what indexes do I have on this test instance. I need show tables so much. Now, what a searcher can do for you, except for searching, of course? Well, it can search, it can group, it can filter, and this is now it's finally pretty easy to explain, referring to Sphinx query language. Sorry, to Sphinx QL, our subset of SQL. We pretty much can do your select, and also we can add a couple of spicy features on top of that select, such as ranking options, or within group order by, or whatever else comes to my mind tomorrow. And we do have a bunch of features beyond basic searching enumerated on this slide, and there's definitely not enough time to cover all of them. And I don't actually remember all of them. I will have to look them up in the documentation. So let's just quickly cover two most interesting features, both related to query optimization. First one, first thing I'd like to cover is distributed searching. And second thing I'd like to mention is multi-query, because I believe these two are the most interesting additional features to just basic searching and select syntax overlay. So partitioning, as you might know, is a Swiss Army knife for different optimization tasks. When you're bound by something, typically you can resolve it by partitioning the data and just having a few workers on your and having more than one worker on your particular task. So if you're bound by full text indexing time, you definitely want to create several indexes and make few indexers work on them in parallel. You're bound by filtering time by some chance. You should partition the indexes based on your filtering conditions. And by far the most frequent case, you've grown past your hardware limits, you're bound by CPU or HDD or both. Then again, you need to partition the data, move it to different cores, to different HDDs, to different boxes. You need to be able to do that somehow. Distributed indexes is the mechanism that lets you do that. It's essentially just a list of a distributed index is just a list of all the local and remote indexes that this instance of search daemon should search when it's requested to search through a given distributed index. And you just list all the local ones, you list all the remote agents, and search daemon searches through all the local ones, and at the same time it tells the agents, the remote agents, to search all the remote ones, then pulls the results from them, glues them all together, sorts them again to bring them back in proper order, and this is it. So a picture is worth 1,000 words, right? Especially my words. So this is a simple diagram of how you partition the data in a bunch of chunks. In this case, you'll get about 10 times better bandwidth, obviously, and also 10 times better latency for all the queries. Just a simple start, but actually can do a two-level query instead of one-level query that is pictured here. And then again, actually every single node can act as a master daemon that does all the remote querying and all the aggregation for you to implement high availability. But I believe we're running out of time. So the next optimization trick I'd like to touch is multi-queries, and it works like this. Sphinx lets you send a bunch of queries packed in one batch, in one network packet. And obviously this always lets you save on network round trip, but in some cases it also allows the internal optimizer to sniff the queries, find out that the queries do have some common parts, and optimize the processing of those common parts. Currently the only publicly available optimization is the case when the query is the very same, when you're querying for the very same thing, but just need different views on the data, just different sorting modes, grouping modes, and so on. Again, this is typical for product search engines. When you're looking for that iPod, you will need to display 10 cheapest iPods to the user, because that's what he's looking for. You also need to look for 3 most expensive iPods, because that's what you're pushing to him, to the end user. You also might want some per vendor statistics, and so on and so forth. And this is the example of how you do that with Sphinx. You just set up a bunch of queries, having different sorting modes and grouping modes, and perhaps limits. And you fire them in one batch using one queries API method. And in this sample, Sphinx will be able to group the queries together to process them as a batch, to perform the expensive full-text querying operation just once, and simply create different result sets of the common full-text search result, intermediate result. That's about it. And just for the sake of pushing, there's also 3 quick magic tricks, 3 big magic buttons. If nothing else helps with Sphinx performance, first, you can cut off searching after you've collected enough results. Second, you can cut off searching after you have spent just enough time on that query or on the talk. Last but not least, you can email me and ask me if I can do something. And the final part of the talk is a war story about the query optimization case we once had, how we made it work in parallel, how we replaced MySQL and learned to love the bomb, but I'm not sure if we do have the time enough time for it, and enough, well, will to hear more of my Russian mumbling. Let's vote. I vote against. Okay, thanks everyone.
Thank you.
Thank you.